Hey guys and girls, my name is Scott, and today we're going to solve the count numbers with unique digits problem on LeetCode. This problem is just a math problem. That's all it is. It's obviously everything we do writing code is math, but this is literally just a math problem straight out of combinatorics. Let's go through the problem definition. Given a non-negative integer n, count all numbers with unique digits where unique digits x where 0 less or equal x less than 10 to the n. So here's the example. N equals 2, 10 squared is 100. So we return 91. So it's all the digits between 0 inclusive and 100 exclusive without 11, 22, 33 because they don't have unique digits. Very simple problem definition. Computing it comes down to if you know combinatorics or not. So here's the background on the combinatorics of how to solve this problem. Then once we get through the background on the combinatorics of how the problem works, we will go ahead and implement it. It won't take very long. So basic combinatorics problem is finding out the number of ways of doing something. Let's abstract it away from this problem. Let's say that I give you 10 hats, and there are 3 people, and I say, place 1 hat on each person. How many different ways could you do that? Well, you have 3 people and 10 hats. The way you do it is you would walk up to the first person with 10 hats in your hand, and you would have 10 options for which hat you would place on that first person. And then you would put one of those hats on their head. You would have 10 options, you'd choose one, put it on their head. You then would go to the second person. You have 9 hats remaining. So for the second person, you have 9 choices. You would place one on their head, go to the third person. You now have 8 hats remaining. You choose one of the 8, place it on the third person's head. So the number of total ways that you could have done that is 10 times 9 times 8. Okay, that's the basics of the combinatorics behind this. And that's all it is. And that's all this problem is. So for n equals 2, the question is, how many different ways can we choose the digits such that they're all unique? Well, we have 10 digits, 0 through 9, similar to our 10 hats. I was clever enough to think that all up on my own. So we have to choose one of the 10 digits. Now, the first place my mind went to with this problem is, well, I have 10 choices, then I have 9 choices, then I have 8 choices, and so on. Which is almost right. It's a little different, though. You don't actually have 10 choices for your first option, do you? Let's say you have for this example, n is 2, so we have to fill 2 digits. We don't really have 10 options for the first one because it can't lead with a 0. There's no such thing in the digit world as 0, 1, 0, 2, 0, 3. So we actually have 9 options for the first choice and then 9 options for the second choice, giving us 81. Well, where's 91 coming from then? Well, the combination that we just computed, 9 times 9, 81, we have 9 choices for the first 2 digits. We assume that the number has 2 digits. We forgot about the numbers that have 1 digit. And for the 1-digit numbers, how many unique numbers are there? There's 10 of them, 0 through 9. So we sum those two up. So 10 plus 81 is 90. 10 plus 81 is 91. So that's how we end up with 91. Again, 9 choices for the first option because we can't choose 0. 9 for the second one. 9 times 9, 81. And then for the single-digit numbers, we had 10 options. Add them together, that's how many numbers we have. So that's the combinatorics behind how the problem works. And for each one, the formula is the same. So for each one, the formula is just you start off with 9 times 9, that's how many options you have, and then it's 8 times, so on and so forth, for each option that you have, for each digit place that you have to fill. So let's go ahead and implement it real quick. What I did was I set up a couple base cases, because the first couple base cases kind of make the math a little funky. So n is 0, we just return 1, n is 1, we return 10, right? We just figured that out. And then n is 2, we return 91. So once we get through 0, 1, and 2, because all those cases make computing the math a little weird, we're into just computing it. So we're going to keep track of a couple things. This is technically a dynamic programming problem. We don't really need to go to the full length of dynamic programming to remember everything that we've done though. We're going to keep track of a running product, because if we don't, we'll be computing the same information over and over again. That's where the dynamic programming comes in. Current product set to 81, because if we're greater than 2, then we would have done 9 times 9, and then the next thing we would multiply by is 8. So I'm also going to set this end variable to be 8 to represent that. So end in this case is going to be the next thing to multiply to product. We need to know what the current value is. We're just going to set that to 91. And we need to know what the previous value was, because that's what we're going to add. And the previous value is 81. Now, why is the previous value 81, not 91? Because in this scenario, we're assuming n's at least 3. And for n equals 2, the value itself is 91. You'll have to excuse my typos. Yes. So why is previous 91? Because for n equals 2, the value is 91. So this is the thing that we're going to sum in when we're looping through and computing this thing. And we're going to keep track of something called k, named it k because it doesn't really have anything better to be named. And that's just going to represent the step that we're at. So once we get past these base cases, 0, 1, 2, we're assuming k is 3 now. So while k less or equal n. So we're just going to loop through and calculate each one of these things. And how do we do that? Well, the running product that we have, we're going to times equal the value on the end. So that's how we keep computing, or how we keep updating the product for the next value that we need to compute. We're going to decrement the end, because this is similar to the hat situation we were talking about. Each iteration we go through, we have one less option. So we had 10 hats at first, we gave one of them away, then we had 9 hats, then we had 8 hats. This is the same thing. Each digit that we go, we have one less digit to choose. So we have 9 digits, then we have 8 digits, then we have 7 digits, then we have 6 digits, and so on. We're going to store our previous, which will be cur, which is going to get updated in a minute. And then we're going to set our current equal to our product, because that is the actual computation of the current value is the product. And then current plus equal to previous, and that actually gets us to the actual value at this step. And then k plus plus as we move to the next step. And once we're done with all this, we will just return our current. Make sure that I got that all set up right. It looks good. Let's give it a whirl. Alright, looks good. Submit. And accepted. Alright. So to run back through what we did, this technically is a dynamic programming problem. Where are we doing the dynamic programming? Well, we're doing it in these variables right here. We're using this memory to remember things that we've done. Because like I said, for instance, like this product variable, if we hadn't done this, we would have had a loop in here where we would have been doing like every single iteration of this loop. We would have been doing 9 times 9 times 8 times 7 times 6 down to whatever this end value is. We would have been doing that computation every single time. So by storing it in this product, we avoid doing that, and then we just update the product by multiplying it by the end, and then we decrement the end. So we keep that running product going. That's kind of the dynamic programming that we're doing, as well as keeping track of the current and previous values. So instead of having to run in and continuously compute this sum, we're just keeping it rolling as we're looping around. So that way we avoid computing the same thing over and over again. So that's the dynamic programming side of the problem. And the other half of this problem is just combinatorics. If you don't know much about combinatorics, definitely some things to go look up on, because they pop up in math type problems like this quite a bit. What we ran through today is just combinations. So like I said, if you have, it's number of ways of doing things. So if you have, just in general, if you have to make 5 choices and they have to be unique, you have to make 5 unique choices, and you have 15 options. 15 options, you have to make 5 unique choices. Well, your first choice, you have 15 options. The second choice, 14. The third choice, 13. The fourth choice, 12. The fifth choice, 11. So the total number of options you have is 15 by 14 by 13 by 12 by 11. And that's how you determine the number of combinations that you have. That's extremely high level stuff. If you don't know a ton about combinatorics, definitely go read up some more on combinations, permutations, things like that seem to pop up a lot in these problems. So that's all for this problem. Hopefully you enjoyed it, and we'll see you next time.